So I've been doing research and teaching in electrical engineering for over 30 years. The University of Idaho has been doing research and teaching in electrical engineering for over 120 years. And we've been an integral part of developing power systems in North America and especially in the West. When the power industry started, you had the same people own the generators, the transmission and distribution lines, and the loads that were fed by them. They basically owned all the wires, they controlled them, but there was almost no communication. There was very little ability to model those systems. So when people started making connections to their neighboring systems to increase reliability, they inherited problems. So if something went wrong with the neighbor system, it affected their system too. And for example, in Spokane at Avista, if somebody in the control center wanted to know what the state of the power system was in Moscow, they would get on a phone and call somebody, and they'd go to the substation and read a meter and tell them. And so they were very conservative with how they ran the system. If any sort of a disturbance happened, that disturbance was determined entirely by physics. But with this growth of connection to neighbors and this growth of complexity, people started doing a lot more with communication between the system. And as computing power improved, it's become a very tightly controlled system. So instead of having the system dynamics controlled by physics and the control decisions made by a human in the loop, now things rely on communication and they rely on automation that can make decisions in a fraction of a second. But with this reliance on communication, there's a downside. Because you have all this ability to control the system is loaded much, much closer to its limits. That makes the potential for this system to be brittle or fragile, which can hurt resilience. So a cyber attack could endanger the operation of this system. A major solar storm could disable some of the communication equipment that's relied on to control this system. Or a major storm could come in and create problems. And so some of the things that can be done are to try to make local, more compact microgrids and to try to come up with resilient control principles to make this work better. I've been working with trying to integrate solar generation and wind generation for most of my career. And as we put these into the system, we have challenges. They're less predictable. You can do weather forecasts, but those don't quite get everything right all the time. And you have to be able to cover any events that happens if a generator trips or a major fault happens or a storm happens. And so those create challenges, and it impacts power system resilience. As we start to see this mix of climate change with changes of rainfall patterns, changes of snow patterns, that interacts with our ability to install solar generation and wind generation. In this part of the country, we rely on the hydroelectric system to cover the variations in the output for these generation types, but they cause other challenges as well. And so one of the things that we do with our research is we're looking at ways to try to improve the protection and control. If we have a large solar farm on a power system and a short circuit happens due to a lightning storm, the behavior of those inverters is determined entirely by controls and by computers. And the way that works is the conventional way of detecting faults doesn't always catch that. And so we're more likely to have interruptions, we're more likely to have problems. So one of our projects is looking at ways to improve the protection algorithms that are used to detect faults, as well as give recommendations to the people who are installing the PV and wind systems to come up with ways to make it so it behaves more friendly with the controls. With the lab we have over here, we're able to simulate a power system and provide measurements that go to this protection and control equipment. And as far as the equipment's concerned, it doesn't know it's actually talking to a computer simulation. It just sees numbers coming into its inputs and it responds to it, and then it interacts with the simulation. So we're able to use that to simulate wind turbines and photovoltaic inverters. We're also using it for cybersecurity research. So you're all familiar with worries for cybersecurity for your computer at home or your phones. It's an even bigger worry with power systems. Other governments and some rogue governments know that we rely on our power system, so they're trying to attack it. And people who work for utilities are fending off and trying to ward off attacks constantly. So the students that work in our lab learn to identify what an infected system might look like, how to mitigate that, how to prevent attacks, but more importantly, if somebody is broken into the system, how to minimize the impacts on the power system. The students that go through our classes and do our research here, almost all of them go out and work in the utility industry or work with selling components to that industry. So they're helping to make our power system more secure and keep the cost of electricity down. Thank you.